Let's start right in with today's keynote, which is given by Peter Sewell, whose third-person bio I haven't learned by heart. You weren't supposed to see this, but well. Peter Sewell is a professor of computer science at the University of Cambridge. Well, if I have to stop, then let me just say he's going to give a very interesting talk. And in the interest of time, please, Peter, the floor is yours. The laptop is also yours for the remaining hour.
Thank you. Thank you for the invitation. Thank you for coming here at the end of a long week in Popple. So this is going to be a very short talk. Can we reason about the security of concurrent systems code? No. More specifically, can we reason that a hypervisor provides its intended protection properties? No. More specifically, can we prove that a production industry hypervisor provides its intended protection properties? Yeah, this is not getting any easier. Could we prove that a really specific production industry hypervisor provides its intended protection properties? For example, PKVM. What is PKVM? A protected KVM is a hypervisor that Google has been building for the last couple of years and still is, with a bunch of people in King's Cross, not very far from here. The idea is that this will protect the Android kernel and other critical components from compromises, especially kernel compromises, after boot. Kernel compromises are not that uncommon, so people really care about this. And moreover, they want to do this in a way which pragmatically can be deployed to all of Android, not just Android on Pixel and so forth. Right? Some of this is already running in some of your phones. Can we do that? This is still not getting any easier. This is getting harder. Can we do that for real? What do I mean by for real? Well, one thing we could do for real would be to write nice papers about it. That's pretty real. But, well, it would be nice to actually verify the binary that runs above the architecture spec that it runs on. The architecture spec is like all of ARM A with its ISA and its concurrency and address translation and everything. It'd be nice to verify the binary that the Google devs off in their office near King's Cross are actually producing, which is built using C and embedded assembly and Clang and lots of tools, which they are not going to change. Arguing that those people should switch to use Concert, for example, that's a non-starter. Can we prove the thing in a way that actually works with the conventional engineering that those people are already doing and are going to keep on doing whatever we do? Well, that would be nice. Can we maintain the thing without infinite expense and a terrible challenge of keeping our research community doing proof maintenance for 20 years into the future? Ooh, that would be nice. Oh, can we do any of that without an insane amount of effort? Clearly, no. Well, definitely no today, but what I want to argue in this talk is this is not out of reach, and it is an excellent focus for research, and the potential payoff very large. Right? So in this talk, I'm going to talk about some of the challenges and some of where we are now, and wibble about some of the open problems, and maybe inspire people to think about the open problems, because there are lots of spare open problems. We're not short of problems here. So who is we? We is a lot of people who are more or less involved in a sort of informal project that we've had for the last couple of years to kind of poke at this problem in various ways. So there's a bunch of people in Cambridge, quite a few of them here, and some of our colleagues in Aarhus and in MPI SWS and in Edinburgh and in Radboud and in SNU. All these people on the left-hand side are kind of on the verification side. And then these people on the right-hand side, who are much more important than us, are actually building the hypervisor in Google and supporting this verification activity and so on. So there's a lot of people. None of these people are working full-time to verify PKVM, but they've all done or are doing, or both, some pieces of this problem, or some things that we think we can fit together. We hope we can fit together. So I have to tell you a little bit about PKVM. And I have to tell you a little bit about ARM. Right? So some of you will already know ARM provides sort of a hierarchy of exception levels, and more privileged code runs at a higher numbered exception level. So there's an EL2 where hypervisors like PKVM run, and an EL1 where the Android Linux kernel runs, and then the rest of Android and applications and so on run at EL0 above that. And in a PKVM system, you might have the Linux kernel encapsulated by this hypervisor, and also other virtual machines, maybe some of them also running copies of the Linux kernel, protected from each other. What's the code like? So, yeah, this is not written for verification. This is written as a bunch of C and ARM assembly code as part of the Android Linux code base. So it's Linux kernel code. It uses a bunch of Linux kernel headers, uses their coding style, all of that kind of stuff we can't change. I have to tell you something about ARM. So how does a hypervisor work? It isolates things using address translation. So ARM, it supports lots of different kinds of regime, but in the one that we're using here, there's a stage 1 address translation, which takes virtual addresses and maps them to intermediate physical addresses, and normally this is controlled by EL1 operating systems. And then there's a stage 2 that maps intermediate physical addresses to real physical addresses, and in this case, those are controlled by the hypervisor. So during boot, the Linux kernel, which these people call the host, hands over control to PKVM. So the kernel is trusted for the initial part of boot, but not after that. And then PKVM makes up a mapping for its own execution, and a stage 2 mapping within which the host runs, and a stage 2 mapping for each virtual machine. And basically what it does is make sure that the ranges of those mappings are mostly disjoint. Right? That's where security comes from. Yeah. And then after that, the host isn't trusted, the guests aren't trusted, but PKVM gives a little API via hypervisor calls, which are exceptions up to EL2, to share pages and donate pages and start new VMs and that kind of thing. Right? So not a very big interface. Okay, so we're going to talk about the challenges. There are lots of challenges. And we're going to do that until I run out of time. It's not a very big audience. If people are mad keen to interrupt, maybe we can interrupt during the talk. Imposing a load on Marco to run around with a microphone. Is that okay?
Gladly.
It's fine. So, first challenge, what is the underlying ARM semantics anyway? So ARM will give you, on their web page, at the moment, 12,940 pages of prose and pseudocode. That's the spec. That is obviously not totally tractable in that form. So we need, an honest mathematical definition of the envelope of architecture-allowed behavior. So there are several aspects to nailing that down. Right? So the first is the sequential stuff. What is the sequential ISA? Or really the instruction local ISA? And that is kind of nailed down, right? So about 10 years ago, Alistair Reed, then inside ARM, shifted them from a purely pen and paper pseudocode to a not entirely mathematical, but machine processed pseudocode. And a few years later, we, working with him, took that and translated it into our Sewell ISA definition language, which is a bit more strongly typed and more convenient in other ways. And from that, we generate theorem prover definitions and executable emulators and relaxed memory tools and what have you. And recently, where we is Thomas? Where's Thomas? Thomas, excuse me. Thomas and Brian have updated this to the current version of the ARM assay, so ARM 9.4a.
That was not executable.
The ASL is within ARM is sort of executable, and this, you compile it to C, it's sort of executable. Right? So for a previous version, where we is Brian and Alistair, ran the ARM internal architecture conformance tests on that C emulator, and you can't say they were perfect, but they were about as perfect as the results that ARM get. One thing you have to understand, nothing here is perfect. Right? You can say, oh, we would love a foundational proof of everything, but you have to understand that, this is not perfect either. You have to kind of balance the effort and the reward. Okay, so this is fine, but it's a teensy bit big. Right, and it gets bigger rather disturbingly fast. So 9.4a, Brown tells me, is 420,000 non-white space lines of spec. Okay, that's not huge by software standards. It's a bit big. So that is massively larger than the hypervisor. Right? The hypervisor boils down to about 20 or 30,000 ARM instructions. Kathleen?
Did you get input from ARM also in this newer version, or did you try to reconstruct yourself how the changes were?
They give us, so these days, they provide quite a lot of this publicly. Actually, here we take sort of some of their we take something which is equivalent to the thing they do publicly and some stuff that they give us just secretly, and we can glom those into Sewell, and then we are allowed, with an agreement with them, to publish the resulting Sewell model under a usable license. Okay. I don't think we've attempted to revalidate this version. Maybe one day we should do that when we have spare time. Ho, ho, ho. Okay, so that's good. And that's kind of everything you might think of. All the instructions, all the exception levels, the translation walks, the debug architecture, all the ISA stuff. That's good, it's great. Why is it 400 and whatever, 100,000 lines? Well, some of you might have seen these slides before. If you just think of one simple instruction, add 1 to the value in that register and put it in that register, then in a nice, easy semantic model, you might write down its semantics as just that. It seems perfectly sensible. But really, that instruction is inside the spec a whole family of add and subtract instructions. And this is actually more or less the complete semantics for that instruction for real. So you have to decode the bit pattern, because this is a machine code semantics, and then you have to decode it some more. And then you have to run it, and this is like parametric on whether you're doing add or subtract or whatever. And inside here, you're accessing some registers. And some of that's kind of straightforward, but this instruction also can apply to the stack pointer. And the stack pointer is a banked set of registers. So at different exception levels, it's a different register, right? So that's indirected via some auxiliary functions. And then you have to read some system registers to know which exception level you're at in order to know which register to access, and so on. And then at the end of the day, you have to actually compute some flag bits and do some honest-to-goodness arithmetic. All right? So, none of that is rocket science. There's just a lot of it. And this is the example that fits on a slide. Okay? This is a register-only instruction. The instructions that touch memory are much more fun. So there's a whole hierarchy of auxiliary functions that, for example, do a memory access at some address. And that might be a big memory access. It might need to be chopped up into smaller ones, which are single copy atomic. So this calls this on a bunch of sub-accesses, and then this mem single takes a virtual address, and it will do some work, and then eventually call what you might think of as a primitive effect as a physical memory read. Okay? So there's a hierarchy of functions in the spec that do that. What happens between here and here is address translation. Well, we care about how address translation works and what it means, so let's have a look at that. So there's a hierarchy of functions to translate a virtual address, and that uses full translate, and that does first this stage 1 translate, which involves, in the ASL, a page table walk reading memory a bunch of times, and each of these accesses are with respect to an intermediate physical address, well, if they're host or guest accesses. So then you have the same kind of deal, translating from intermediate addresses to physical addresses, and each of those might have to read memory a bunch of times. And the first accesses are translated by the stage 2 translate too. So you have to read memory a lot. And this is, in any specific context, this is not super complicated, but then there are, umpteen different configurations of everything, which make it extremely complicated. But we know what it is, because they tell us. It's good. Okay, so we kind of know what the sequential instruction local semantics is, but we know that ARM is not a nice, simple SC machine. Right? ARM has a relaxed memory model. So we need to figure out what that is. And some of that, we and other people have figured out over the years, and there are these relaxed memory models in different forms and with a lot of different litmus tests illustrating particular relaxed behavior for the user mode concurrency. I say user mode, it's not really EL0, it's all the things that don't involve features that you can't do at EL0, like exceptions and address translation and instruction cache maintenance. You can do a little bit of that, and so on. Right? So this was really only the merest beginning of understanding what the underlying relaxed semantics is of the platform that we're building above. Right? Because you need, to talk about a hypervisor, you need to know how all of these things work. Right? So for the last couple of years, we've been working with ARM to try and nail down what the architectural intent for these is and capture that in precise models. Who is we? We is Ben and Thibaut, and other people. So there's a nice paper in ESOP, and then another nice paper in an older ESOP, and a bunch of work in progress, because this nailed down a lot of things, but not quite everything. And then a bunch of work also with OHAD on exceptions, and then also a bunch of mostly complementary work going on inside ARM with JavaScript et al. So none of this is kind of totally nailed down, but it's kind of getting there. Right? It's kind of approaching a decent foundation for verification. So I don't want to talk about this very much, but just to give you some very vague flavor, this is one of Ben's relaxed virtual memory litmus tests that just illustrate some particular, semantic design question that you have to think about. And I'm not going to even read this out, but it's a test. It sets up, some page table initial state, somewhat symbolically, and it has a couple of threads, but now the threads do TLB maintenance, and there are exception handlers to figure things out, and so on. And you can see in the execution, there are a bunch of reads and writes and a bunch of edges, but some of these reads are now translation reads related to the instructions that did the address translation that created those reads, with a bunch of amusing relations over them. And it's totally fascinating talking to the architects about this, because you're up against what the architecture design is and why it is what it is. Right? And lots of that is, of course, totally clear to them because they've been designing this architecture for a long time now. And then every so often you say, hey, should this be allowed or not? We have to decide. You're making a model. You have to decide everything. And they say, good question. And then, these are the other pictures in Ben's thesis. It's like humanly doable, but there's quite a few things you have to pay attention. Okay, so I said these are not definitive. There are interesting open problems. So there are some open questions about what the semantic should be, not so many. There are probably quite a few open questions about the interactions between these different features that we've not seriously considered yet. It would be good to have better testing and test generation. We would like to converge with the ARM internal work. All of that is kind of in progress. And I think already we have a sort of decent foundation for quite a bit of verification work. Right? A lot of the things we've done already are not going to change very much. Okay, so we have something almost to work above. Whew, that's something. Can we potentially reason about any of that? Be nice. I'm sorry, I'm out of order. We have two pieces of the foundation. Are they joined together? Surely that's trivial, you say. We just take this paper, and we take that paper, and we take a big stapler, stick them together, and we're done. Oh, if only. So we have previously glued these things together in software tools, right? So all these different tools by us and by Jad and Luke have glued together some version of some relaxed concurrency model with some version of some instruction semantics model. And over the years, these have become more elaborate and more full. So this Euler axiomatic tool by Alistair Armstrong glues together axiomatic models with the full ARM or RISC-V ISA, so win. The RMM tool uses the full RISC-V ISA, but for engineering reasons, still only fragments of old ARM. But that's good, but we don't have, and nobody has had, an integrated mathematical definition of that combination, right? We have not yet drawn that little line. So right now, even as we speak, Thibaut is trying to draw that line to make a mathematical definition in what we shall now call ROC to precisely define the set of allowed multi-core executions in a way, hopefully, that will be reasonably reusable over future time and not change too often. I mean, surely we will have to change it a bit, but we're trying quite hard to engineer that to make it robust. And there is a very interestingly shaped line, because you have to understand the information that the ISA semantics has to expose to the virtual memory model in order for it to say what it needs to say without it being insanely complicated. And it has to be nice enough in style to support proof and still be executable enough to run tests. Right? Otherwise, we can't validate it ever, and it will be wrong. Okay, so that then is this foundation. And now we ask, can we reason above it? Let us be humble and set our sights low. Can we reason about the sequential part? Okay, that's not very humble, because it's a 400,000 line definition. But maybe we can chop the problem up a bit. So there are two kinds of problem here, which are really very different, right? So one is, can you reason about specific bits of binary code? Or maybe code abstracted on some relocations or some register names or some immediate values, but more or less specific bits of binary code. And can you reason about that just in a sequential, sensible fixed translation setting? Well, I mean, maybe you could do that just sort of straight above the definition in Approver if you were very strong and much cleverer than I am. But all that complexity in the instructions really gets in the way, right? So Michael Samler and Angus Hammond, I think neither of which are here, came up with this scheme, which we call Ilaris, a couple of years ago. And there are two ideas here. So the first idea is to notice that even though for instructions like that you have that whole page of sale, if you know that you're working on a specific opcode or on an almost specific opcode, and if you know that you only care about the semantics maybe at EL2 and maybe under some other assumptions of other system registers, and maybe on some assumptions that some addresses are aligned, so you won't generate multiple accesses for a memory access, just one single copy atomic access, then this Euler symbolic evaluation tool by Alistair can take that page of sale and simplify it down with symbolic execution to a nice, easy-peasy little trace. Right? So we get rid of a lot of that static complexity with this symbolic execution. Okay? And then you can take those traces and you can feed them into Iris. Well, really, you can instantiate Iris with the language of those traces and make some proof automation above it and actually reason about machine code. Win. And even machine code that does some systems-y things, but in the sequential world. Right? So Angus proved a fact sort of like this about the first 49 instructions of one of the PKVM exception handlers. Right? So this is a piece of code actually written in assembly that runs when you first take a fault into PKVM from the host. Right? And you can see there's a precondition and a postcondition, and these are both really written down in Iris, but I'm not going to tell you what they are, except to say some of them are a teensy bit subtle, like this one. You know, the next two words of the stack are used by this handler, so we have to own them, and we have to be able to compute their addresses without an overflow in the machine semantics. Right? So there's lots of things like this. You know, they're all little things, but you have to actually have them all nailed down. Open questions. Does this scale to big enough examples? Maybe. Maybe we need to do something different. Could we do it without relying on this external symbolic evaluator? That would be nice. It's not essential for the level of assurance that we think is possible at the end, but it would certainly be nice. Yeah, so, don't know. What about the other half of this sequential problem? Can we reason about arbitrary ARM instructions? Why do we need to do that? We have a hypervisor. Well, we have a hypervisor, but we also have all the host and guest code, which is untrusted. We want to be able to reason about that. But we do not want to reason about that in terms of the full ISA all of the time, because that would be quite annoying. Right? So what we want to do instead is characterize the potential behavior of arbitrary code. And I mean, the hypervisor has to work whatever it does. So this cannot be a very complex property. But for example, you might want to know that in the configuration that PKVM is running, the EL1 and EL0 memory accesses are to end up being to physical addresses which were produced by a legitimate translation. Right? So that's a fact about the whole 430,000 lines of ISA spec, but it's not a very deep fact. And conveniently, Thomas and other Thomas have been proving that kind of fact about this cherry-enabled ARM, Morello, and the same kind of thing you can use for this. So this is mechanized proof in Isabelle, honest to goodness proof of the sale, about the sale-generated Isabelle. Yay to Isabelle and Thomas for being able to handle definitions of this scale. It's not totally trivial. Open questions. It would be nice, not essential for us, but it would be nice not to have two different provers in the story. Can you do similar proofs in Rock without it complaining? Rock is not very friends with at least the current sale to Rock export. It just explodes terribly. Totally can't handle it. Maybe we could do differently, maybe with a deeper embedding of the sale into Rock. I don't know. Good question. Okay, so that was reasoning sequentially. Dominic?
So you have these 2A1 and 2A2. Have you thought about how to connect the two together?
In a hand-wavy way. Some of that, I think I will draw you another cartoon picture later that will speak to that a little bit. I mean, I kind of understand how a proof might go that connects them together. Before we get to that, what about the concurrent part? Okay, so for user RMA, we have models in these different styles. Operational, axiomatic, promising, all good in their different ways. Proved equivalent for some fragments. That's great. But these models, not so much the models, but really the ARM architecture is hopelessly non-compositional. Right? Just everything is totally global. Right? These only define the semantics of whole programs. And for axiomatic models, kind of the others too, they only define the semantics of complete executions. Right? And this is kind of intrinsic to the architecture because ARM allow this load buffering shape. You can have cycles in PO plus RF. Right? You can have perfectly allowed executions like this in which two reads read from the program order future of another thread. So you can have, there is no prefix of this execution, no PO prefix, which is closed under RF. Right? So the prefix, I mean, it's not sort of nonsense, right? It's just intrinsically not very compositional. So that's a bit of a challenge. Worse, when you have mutable address translation and you have self-modifying code, both of which we have here, and this may be a shock to you, there isn't a program. Programs don't exist. Right? There really isn't a program. There's nothing to do compositionality on, okay, a priori. There's just an initial machine state. Okay, that sucks. Well, no, it doesn't suck. It's great. It's a lovely opportunity with interesting problems. Okay, can we pretend this doesn't exist? Regrettably, no, because PKVM is quite concurrent with itself and its guests. Right now, within itself, it's kind of simply locked in some ways, but that is getting worse even as we speak. Well, at least on Monday it will be, when the people in the Google office make it more relaxed. Right? But it is manipulating the address translation it uses for its own execution. It's dynamically loading some initial code. It manages these address translations of the host and the guests, but those are doing translations while it's managing the page tables and so on. And it has to do enough TLB management to ensure that some key ARM architecture requirements are never broken. Right? So we have to be able to reason about this stuff, but nonetheless, most of the reasoning about the C code of the hypervisor, you want to be under the isolated, sequential, sensible, fixed translation assumptions. Right? So how can we establish that that's a sound abstraction, and for the bits of concurrency that are not like that, how do we reason about those? Those are good problems. Well, let's look at it first. So this virtual memory semantics of ARM, as Ben has explained to us, is insanely complicated. Well, not insanely, it's quite complicated. But the way PKVM uses it is kind of special. So for example, it's good, well-behaved code. It is not going to violate this ARM break before make discipline. Right? So we think we can, and Jean-Pierre Faribault and Ben have been working away to build what we call a simplified model. We do need a better name for that. A simplified model which is kind of like a data race-free SC model. Right? We can build into this model that the hypervisor is not allowed to violate break before make, for example, and just not give semantics in that case, and thereby make that a proof obligation on the higher level verification. And hypothetically, we can prove that sound above the architecture, and then that gives us a basis for reasoning sequentially about the bulk of the C code. Open problem? Well, actually do it. What about the remaining tricky cases? Well, we kind of think it would be nice to have a program logic above that simplified model. The model doesn't exist yet, so obviously we don't know how this will work. But conveniently, Zhongyuan, who is here, and Angus, who is still asleep, have figured out how to do a program logic above the ARM user axiomatic model, which for quite a few years we have thought was just impossible. So, yay. And it's even done in a way which is kind of generic in what the axiomatic model actually is. So we have some hope that this will be generalizable to other axiomatic models, or in particular to some presentation of this simplified model that we were talking about. There are lots of open problems. So this already still doesn't cover the nice reasoning about coherence. It's really a logic for reasoning about the OB order, the happens before order of ARM. And it does use some version of the honest interface to the ISA, but it isn't actually plugged together with the full ISA yet. And then we need to generalize it to the system stuff. So those are all big questions, but identifiable, articulatable questions. Okay, now we return back to Dominique's question. How do we envisage some of these pieces might be fit together into a proof? I emphasize envisage. Okay, this is entirely vaporware. But okay, first we have to imagine what the spec will look like. What is the top level spec of a hypervisor? Right. Well, this hypervisor provides an abstraction to the arbitrary hosts and guests, which is more or less the same as the ARM abstraction. Right? All the instructions, all the normal ARM concurrency, stage 1 address translation, all the stuff that EL1, all the system stuff that EL1 can do, all of that is just, directly provided by the hypervisor to their clients. Right? So it provides an abstraction just like the ARM spec, which is, the ISA glued onto the concurrency model via this nice interface, except that these stage 2 translation functions that I showed you the types of, and the semantics for EL exception and return to and from EL2 have to be ripped out. That's kind of easy because there are nice function interfaces within that spec to do the ripping along. And some other now irrelevant EL2 state has to be ripped out of the model. And the concurrency model has to be extended with sort of new API events for those things and new magical semantics for how the hypercalls behave. And that magical semantics is essentially the more or less hardware thread local spec of each of the PKVM exception handler pieces. And then there's some other complications which I shall skip over. So that's sort of the spec, and then one can think about the correctness statement that one would aim for. There are, I'm sorry, quite a lot of words on this slide, but just sort of quickly, what you would like to prove is that for any supported hardware configuration, that's already a fairly big quantifier, for any legal choice of the initial runtime, where it's positioned in memory and things like that, that's not too big a deal, although there is an engineering challenge. For any contents of the PKVM initial state that satisfy a great big fat invariant, that we plan to test, not prove. For any arbitrary content of the non-PKVM initial state, any complete execution of the underlying machine semantics together with these two gives you a sort of similar execution of this right-hand semantics, except we'd like the EL2 parts replaced. It's sort of the concrete theorem that you think you should be able to prove. Yeah? Or in pictures, any execution of this thing should be, with some erasure and slight other surgery, be an execution of the nice top-level spec. And this uses, so we aim in the course of that to use this simplified model. So what's the soundness of the simplified model? So the simplified model sort of just fits in the same place. Right? It has the same concurrency interface, and under the assumption that the ISA satisfies the whole ISA properties proved in Isabel by Thomas about translation, then any execution about this should be an execution about that. And this is a very lovely picture in a way that may not be totally obvious, because all of this yellow stuff doesn't involve anything about the instruction semantics, which is large and unwieldy, except those properties. Does that slightly answer your question? And then the proof of this will involve some sort of DRF-like reasoning. Dominique looks skeptical. Perfectly properly. There are a lot of moving parts. I mean, it took us a while to even get to this level of clarity. Yeah. Okay, so this part is definitely vaporware, but it's like not totally implausible. Yeah, that is an open problem. Okay, so now I'm going to have to abbreviate quite a bit what's on the slides. But I've been talking about ARM, but you mostly don't want to reason about ARM. Most of the code is in C. You want to reason about the C in its terms. Otherwise, maintainability and proof effort, obviously a non-starter. For C, very conveniently, we just happen to have in our back pockets a semantics of C, which Caven and Marion has been working on these many years, and it's quite well validated. It's good. We've got memory object models that we can believe in. It's good. Thanks also to Rodolphe and Michael in MPI at the time for some of that. Can we reason above that? Lots of people have done some reasoning about C, many of them in this room. And there are lots and lots of cool ways to do it, all of which have done, impressive examples. But I think it is, probably none of those people would disagree, we have still not reached the happy state where this is nice and easy and maintainable and doable even for low-level Linux kernel idioms, not compcert C, and integratable with all of this concurrency stuff. So there is a whole big story about this, developing separation logic refinement type systems to try to do slightly less annoying reasoning about C. And we've had 2 experiments which are ongoing, CN and refined C. CN by Christopher Poulter and Dhruv Makwana and Thomas Sewell and Caven and Marion and Neil Krishnaswamy, who is here, and refined C by our friends in MPI, Michael Samler and Rodolphe Lepigre and others. So these are both good. If I just show you very quickly some CN stuff, you annotate code with separation logic assertions, essentially, but in some quite limited fragment to try to make the proof automation reasonably predictable. That's the top-level punchline. And it kind of works, even for some of this low-level code. This is one of the functions from a PKVM buddy allocator, which does exclusive OR on pointer bits and lots of integer pointer casts and what have you. And it's kind of a readable spec, and with some predicates and things that you can understand, and it kind of works. It doesn't work great, and there is a very open problem. Is this going to scale to all of PKVMC, or do we need something substantially different? And then there are lots of other more specific open questions, which I will gloss over. You will notice this is hanging in midair compared to this. You will have noticed that. We imagine And Thibaut and I and a master student from Munich, Mette Polet, have done some experiments on translation validation to relate these two. And this is interestingly different from the normal translation validation problem, because here, in principle, you have a whole CN verification of the above in a nice separation logic, which we can exploit. And we have like all the debug information for the binary produced by classic Clang, which we can exploit. Right? So maybe we can do that, but we haven't done it. That's a big question. Okay, up to now, yeah, soon. I guess we started a bit late. Did we start late?
Yeah, 5 minutes late.
Okay, maybe I'll not be totally out of time. That would be unusual. Yeah, this is like a classic verification story. Okay, we should never do the classic verification story. It's no good. Right? I mean, it's good for writing papers in Popl. It's really good for that. But you have like this terrible cost-benefit function, right? And this room gives me like the ideal setup in which to explain it, because you have this line. So vertical axis reward, horizontal axis effort, right? And it goes along this line, further along this line. Each of these is like, you know, a very sad PhD student. And then it goes along this line, and then, yeah, those things are very sad postdocs, and it goes along this line. This thing is a very sad funding body, and that thing over there, a very sad industry collaborator, and then it goes along here, and then it goes along here, and then it goes along, and then it goes over here somewhere, and then, if you're sufficiently fortunate and skilled and everything, there's like a step function to, yay, we've got a proof! It's terrible. It's just totally terrible. And in all of this time, what you could say to your, you know, conventional engineering development collaborators is, yeah, well, just be patient. Just hang in there. We're working on it. We are working on it. See these papers that you don't want to read? We're working on it. It's terrible. We should never do that. We should never do only that, right? So what do we have to do to engage with a development team? We have to understand how they develop things. How do they develop things? They do test and debug development. And they're very clever, so they can make that work. They are really clever, and they can make that work really quite well, but that's what they do. So we have a scheme here to, instead of just do all of this proof, actually make these specs very straightforwardly testable. And the scheme is not entirely in place yet. Rini Banerjee, who is not here this morning, is beavering away working on that. It turns out that the restricted expressiveness that makes CN good for proof, thanks Neil, also makes it rather testable. Right? You don't have to go away and say, oh, I will just search for an existential split of the heap now, right? Which is a rather tiresome thing to do. So we would like to provide them, and we think we can quite soon provide them with an infrastructure in which these rather rich specs can nonetheless be tested at runtime in conventional execution. Indeed, in conventional execution, integrated online with the hypervisor code at EL2, a bit slowly, but nonetheless, or potentially running offline, which actually the devs seem to prefer the idea of. And then, that together with a hopefully readable specification language, which is suitably but not offensively noisily integrated with the C, is at least a plausible way that we can get a slightly better graph that maybe goes up a bit, going from over there to over there. There's some open questions. Make it really work. Actually build infrastructure for driving the thing. We've got some of that. Script good tests. Generate good tests. A whole lot of interesting questions there. Some of which we're discussing with our UPenn friends. Lots of things one can do. Okay, so far, I haven't actually talked about any verification of the actual code to speak of. Obviously, there's going to be a fair bit of that. Nor have I talked about how one nails down what this top-level spec actually looks like in any detail. So we could spend the next however long, polishing up all of these tools and then do that. Or we could try it now. But we haven't got any tools that work. How can we write a spec with no tools? Oh, we could just write something on paper in a theorem prover. Oh, but then we can't test it and nobody except us can read it. So instead, we do a mad thing, which I'm very proud of, which is to understand that your favoritist programming language. What's your favorite programming language?
Rust.
You're all wrong.
C.
You win. I'm not sure what you win. A lifetime of pain, probably. But C, even if it's not all of your favorite language, it is the dev team's favorite language, or possibly least favorite language, but it's the one they use. C is a great specification language. C is just the bits as a specification language. It needs zero investment in weird, wonky tooling, or zero investment in educating people how to read specs. And you can just run it. It's great. So we prototype the top-level specification of PKVM in executable C code that runs at EL2 and everything with, all the integrated with the concurrency model of the hypervisor. So Ben and Thibaut and David Caliper-Mershignac and I and Kaven Mumerian have been working on that recently. And we now have a top-level specification of the whole thing that is, well, A, is very instructive for us. That's a first benefit. But B, does actually run. We haven't tested it very much yet. If this conference had been a month later, maybe we would have. And you can't prove anything about it. But these are specs which you can discuss with the dev team very straightforwardly. And the scheme we have in mind is to translate these, hopefully rather straightforwardly, into the CN spec language, which may need to be jazzed up in some minor ways, and it will need a somewhat fancier separation logic at the end of the day. But a lot of this should just translate rather directly. Right? So, some kind of assertion checking on steroids, right? So we really compute in C reasonably efficient C representations of the abstract state that you might have written down as a bunch of rock data types if you were that way inclined, right? So we walk over the honest to goodness page tables at the appropriate points in the code when the appropriate locks are taken and compute their interpretation as finite maps and such like, and manipulate those in the spec. So you get quite nice specs in which the spec of a hypercall says, well, you take this thing away from that page, that address translation finite mapping, and you add it to that one when you donate a page from here to there. Looks good. Okay, high time I stopped. Can we reason about the security of concurrent systems code? Definitely not. But kind of maybe one day soon. Right? I wouldn't wish to make too strong a statement, but we are very seriously aiming at that, and I think it is feasible. The sort of slightly wider point that I want to make is that there are a whole lot of interesting problems, like really interesting problems, and ones that people actually care about out there in the world, not just in the POPL community, and that one wouldn't even start to see some of these problems until you at least try in your imagination to try to stitch these things together at scale, and to, at least aim at all of the sort of for real version characteristics which I mentioned here at the beginning. This is, of course, only one scheme, and Gregory and his fellows will tell you about some quite closely related but different schemes in some other talks, and other people have done other verifications of hypervisors. But I think it's very instructive to try and, draw this, make this, this is a cartoon picture, right? But to try to make this cartoon picture a real picture is quite educational and fun, and potentially even useful, who knows. With that, thank you for your attention.
Well, we have time for questions.
Hey, Peter, fantastic talk, as usual. Two questions. One is this green part relating C to ARM. What kind of verified compiler can you use? Is Adopt Concert has all the features that you need for that? And the second question is about what about other hardware manufacturer? Like how much of this work effort can be adapted for Intel or NVIDIA, whatever?
So for the first question,
Can you repeat the first question?
So the first question is, for this translation validation part, what kind of verified compiler could you possibly use? And the answer is no kind of verified compiler, because Android is built with Clang. It will keep on being built with Clang. This is kind of immutable. So we really do imagine doing translation validation, not compiler correctness proof. I mean, as I said, we have not remotely done this. We've sort of dabbled with it a bit, and Corridor has some pictures with the control flow graph of a predecessor of PKVM at 00 and 01 and 02, and we kind of scratch our heads and think about that. I think it's sort of general translation validation of Clang is still a very open problem, although I think even that people could do a lot more than they have done if you do it by phase, by optimization pass very carefully. For this, it does sort of seem within the realms of plausibility that we can do it. I mean, maybe with some optimization turned off, but if you do that, then at least you limit any errors in PKVM to the there are optimization bugs problem. We kind of have to do this because, I didn't say this, this is the only semantics at the end of the day that we can get real confidence in, especially for the system stuff, right? We don't see ourselves, I mean, this is pretty well validated, but extending, you can't directly extend that to all the system stuff. Okay. The second question I now forget.
It's about Intel.
Oh, yes. How much of this would apply to other architectures? So I think a lot of the tooling would apply. There is now a chunk of x86 Sewell model that covers some system stuff which the ACL2 people developed, which we've imported into Sewell, for example. The concurrency model is quite different. No one has looked at the relaxed virtual memory of Intel. I have no idea what that's like. This stuff would be kind of similar. For RISC-V, it would probably be pretty similar. A lot of this is common.
I think we have time for a couple more questions. Well, yeah, we can go over time. No worries. I think it was first.
Yeah, thanks. Thanks for the interesting talk. And you've presented a bunch of very difficult challenges or problems. And one of the ones you mentioned at the beginning, I was still curious that you didn't resolve how you would maintain all of this, right? Like you have one version of the microarchitecture that you have now. What happens when a new one comes in? What happens when they continue to develop the hypervisor? How can we hope to maintain this without a lot of pain, like you said?
So excellent question. How can we hope to maintain any of this without going mad? So one part of this is to, I mean, broadly, one would hope to make the things which are liable to change as predictably automated as possible. And the other thing is to make the verification of the C code, like, so this is CN annotated PKVM code. So the developer, or really the verifier, has to write this. But I think we can plausibly hope that the developer can read most of this and talk about it. And then, there would be a burden in updating this when the code changes, no question. But hopefully a rather smaller burden than if you had a whole enormous, very low-level proof. So you would aim, in another instance, to make the simplified model of abstracting from some of the virtual memory properties to let you ignore fine details in the virtual memory semantics. And it does to some extent. But I'm not claiming that a magic bullet has been provided.
So just a question also on composition between what you do at the C level, and I guess some things have to be done at the assembly level. Like, how do you see that going?
Okay, so the relationship between C and assembly is really interesting. So the first thing to say about it is that except for that exception handler, let me just get the cartoon back again, except for that exception handler that I spoke of, all the assembly in the code is very special. Right? It's just inline assembly to do a TLB maintenance or a barrier instruction. Right? So we do not want even a generic composition of arbitrary C and arbitrary assembly that mutates C data structures. Fortunately, not necessary for this scenario, although that's also a good thing to do, but there isn't the kind of code that the devs write for this. More generally, okay, so we might have we do have some separation logic, essentially assertions annotating the C code up here. And the idea which Mate Polak pushed a bit in his master's dissertation as an experiment is to take those assertions which are about the C abstract machine state and reinterpret them about the ARM state using the debug information to tell you what they mean. Right? That seems to me a rather straightforward thing that people should have done 10 years ago. And it's super powerful because you get to know sort of automatically the concrete thing that has to be sort of automatically verified down here if you want to do the translation validation. And down here, I mean, ultimately this separation logic will have to know some things about the simplified model for the TLBIs and so on. So that will appear in our reasoning about this. Well, actually about our reasoning not above this, but above this together with the simplified model that I spoke of. Joe.
Yeah. Do you have a sense of how many security vulnerabilities rely on some of these very low-level details? Like, let's say I was very naive and I wanted to do my verification assuming SC. Are there attacks that we know of that I would miss in doing my verification?
So my feeling is there are not very many known relaxed memory dependent attacks because there are lower hanging fruits for attackers to go for. If we were aiming for sort of a security bug finding project, we would be doing different things. Right? We really are aiming for high assurance at the end of the day. Are there any bugs at all? So we have not done enough verification to even have in principle the possibility of finding bugs, but we have done quite a bunch of reading of the code, especially in writing these top level specs. And Ben and Kevin and Thibaut and David came up with a list of like 7 questions that we sent to the devs quite recently, of which about half of them or something, maybe a bit more than half, they said, yes, that's a bug. And one of them was, oops, in resolving some Git conflict, they had managed to omit the TLB maintenance during initialization. I mean, that's probably exploitable, although there might be easier exploits.
Well, since there's no further question, thanks again for the wonderful talk, Peter.
Thank you.
I wanted to ask if speculative execution changes any of this picture, but that might take too long.
So a lot of this relaxed memory semantics arises from speculative execution. Right? I mean, there's another thing about speculation barriers that we're not in a position to reason about.
Right.
There should be a. Oh, do you want this?
Yes, please. Thank you.